Okay, third and final video of these applications. It wasn't exactly a random choice. I picked those that weren't overly complicated. The other two that are there are very interesting, and there are really some other interesting applications other than the ones we found. And on the homework, I'll also ask you to look online, see if you can find another interesting application. This one is balancing chemical equations. Many of you have done this. This is example 5 of section 1.3. How does it work? Well, like a lot of applied problems, you start with something that has no mathematics in it. Caffeine oxidizes to yield carbon dioxide, water, and nitric oxide. So you do a little chemistry, and this is caffeine, C8H10N4O2. So this is the caffeine molecule, what composes it. Oxygen, this is molecular oxygen. CO2, carbon dioxide, water, nitric oxide. So where is the math? Well, it's almost there now, because what you want to know is how much of this plus how much of this yields how much of this, how much water, how much nitric oxide. And what that means is that you want to balance the atoms on each side. So you want things to, you want all of the caffeine to add up with all of the oxygen and give you no residues left over, and it forms how much of this. You want the atoms to balance out. So on the left-hand side, you analyze this one atom at a time. So we'll look at the carbon first of all. On the left-hand side, we've got 8 X1 carbons. And on the right, and then that's it. On the other side, on the right-hand side, we've got X3 carbons. So there's our first equation. Hydrogen is similar. On the left-hand side, we've got 10X1 hydrogens. On the right-hand side, we've got 2X4 hydrogens. And this continues. You have a total of, let's see, 1, 2, 3, 4 different atoms represented in this entire equation. So this will give you 4 equations and in 4 unknowns. And so eventually you get a system of equations. And the system of equations is 8X1 minus X3 equal to 0, 10X1 minus 2X4 equal to 0, and so on. 4X1 minus X5 equal to 0. Oh yes, we've got more equations than, on more variables than atoms, because the variables go with the compounds that you get, not with the individual atoms. And then the last one is more complicated, 2X1 plus 2X2 minus 2X3 minus X4 minus 2X5 equal to 0. This will give you an AC matrix, augmented coefficient matrix. Type it into Mathematica, row reduce it, and you will get the solution. There's one thing here that's, again, something to pay attention to that has to do with the problem, not so much with the mathematics. But when you solve this, you will find, for example, that X1 ends up to be 1/4 S. S is a free variable in this case. So X1 is 1/4 S, but X1 stands for a whole number of atoms. This is the number of atoms of carbon. So this should be a whole number. So that means any S will actually give you a mathematical solution, and S that is will give you a solution chemically so far is one of these. It must be divisible by 4 in order that x1 is a whole number. And each of the variables, x1, x2, x3, x4, x5, will tell you a similar thing, and then you want the least common multiple of all those numbers. I think in this case, 8 will give a whole number of solutions for all of the variables. That's sort of the only problem that you run into with these balancing chemical equations. All 3 of these are pretty straightforward, but I'd like you to know how to work them, at least 2 of them. Thanks a lot. See you tomorrow.